This is the third lecture on multi-electron systems. Today we are going to be looking at the first order correction to the energy using perturbation theory and apply the same to the helium atom Hamiltonian. So let's say that we have a Hamiltonian which has eigenfunction psi and eigenvalue E. Now let's say that this Hamiltonian can be broken into two component Hamiltonians. The first of which is exactly solvable and has eigenvalues and eigenfunctions that we know. And the second part of the Hamiltonian renders the total Hamiltonian insoluble and is known as the perturbing Hamiltonian. Now, let's say that the exactly soluble Hamiltonian has the eigenfunctions psi 0 and eigenvalues E0. And let us assume that the eigenfunctions of the total Hamiltonian can be written as a sum of the eigenfunction of the exactly soluble Hamiltonian and a correction term. Similarly, the eigenvalues of the total Hamiltonian, let us assume that they can be written as a sum of the exactly soluble Hamiltonian's eigenvalues and a correction term. Now, here what we will do is to find out delta E. That is the correction to the energy. To do that, what we do is to take the total Hamiltonian, that is the sum of the exactly soluble Hamiltonian and the perturbing Hamiltonian, and apply it on the eigenfunctions of the total Hamiltonian, which was expanded as a sum of the eigenfunction of the total eigenfunction of the exactly soluble Hamiltonian plus a correction term. And this is going to be equal to eigenvalue times the eigenfunction. And the eigenvalue of the total Hamiltonian, as alluded to in the previous slide, is the sum of the exactly soluble Hamiltonian's eigenfunction plus a correction term. Now what we do is to expand the terms on the left hand side and the right hand side, and what we get are the following terms. Now what we can see is that some of the terms are too small to be considered in the next steps. The first term which is too small to be considered in the next step is delta E into delta psi. This is because delta E, it is an assumption that the perturbation to the system is quite small, and hence we expect that the change in the eigenfunction of the total Hamiltonian from the exactly soluble Hamiltonian is also going to be small. So taking a product of the change in energy as well as the wave function makes it an even smaller quantity. And this is why we neglect this term for the upcoming steps. The next term which we are going to neglect is the perturbing Hamiltonian acting on delta psi. Again, the reasoning goes the same way as we did for the previous term. It is because it is an assumption that the perturbation to the system is quite small, and delta phi delta psi is also a small quantity since the perturbation is small, and hence we expect this quantity to be small as well, and hence we neglect it. Finally, we see that there is cancellation of some terms on the left hand side and the right hand side. This is because S0 acting on phi 0 is nothing but E0 times phi 0, which follows from the eigenvalue equation, meaning that it is the meaning that at 0's eigenfunctions are phi 0 and its eigenvalues are E0. Hence, we can safely cancel these two terms. Now we are left with a relatively simpler looking expression, and what we do is to collect the like terms and get an expression that looks like this. Now what we do is to multiply the complex conjugate of phi 0 on the left hand side and the right hand side and integrate it over all volume. Now there's a property of Hermitian operators that we can use to remove even more terms, and once we apply that property, what we see is that one of the terms in our expression goes to 0, and this is because at 0 times phi 0 is equal to E0 times phi 0, and this follows from the fact that psi 0 is an eigenfunction of the exactly soluble Hamiltonian, and E0 is an eigenvalue of the exactly soluble Hamiltonian. And as a result, what we have is that if I go to the previous slide, what we see is that this term can be removed since it equates to 0, and as alluded to earlier, this follows from the Hermitian property of the operator. Now the Hamiltonian is a Hermitian operator, and E0 is a constant. Hence, the total operator at 0 minus E0 is also Hermitian, and as a result we can do this. Finally, what we see is that the correction to the energy becomes the expectation value of the exactly soluble Hamiltonian on the perturbing Hamiltonian, which is H1. And as a result, the total energy can be written as a sum of E0 and delta E, where delta E is the correction to the energy from the exactly soluble Hamiltonian's eigenvalue. Now let us try to apply the same for the helium atom to get an estimate for its energy. Now let us look at how we can write the Hamiltonian for the helium atom. We have the kinetic energy for the nuclei. After that, we have the kinetic energy for the 2 electrons Then we have the electron-electron repulsion term, which runs from the indices going from 1 to 2 and j equal to 1 to 2 as well, but we take care of not having repeating terms by imposing the condition that j is greater than I. And finally, we have the nucleus electron attraction terms. And for the nuclei, the index A runs from 0 to 1, runs from 1 to 1, meaning that there is just one term. And for the electrons, it runs from 1 to 2, since there are two electrons. And this is how a Hamiltonian looks like when we do that. And as so, this is our kinetic energy for the first electron, kinetic energy for the second electron. This is our electron-electron repulsion term. This is our electron nucleus attraction term. This is our electron nucleus attraction term for the second nuclei. Sorry, for the second electron. So, one term is missing here, that is the kinetic energy of the nucleus. And this is because this Hamiltonian has been written from a frame that is fixed on the nucleus, and as a result, the kinetic energy of the nucleus becomes 0. Now, delta E, that is the correction to the energy, is going to be the expectation value of the exactly soluble Hamiltonian. Expectation value of the perturbing Hamiltonian, which in this case is the electron-electron repulsion term, on the eigenvalues of the exactly soluble Hamiltonian, which in this case is phi 0. Now let's say we want to find the correction to the energy for the ground state, that is the state in which both of the electrons in the helium atom are in the 1s orbital. Now, for that, what we do is a similar trick that we have seen in the previous lectures. So, when we don't have the 1 by R12 term, what we can do is to separate the variables. So what we can do is to take these two terms and take these two terms together, and our eigenfunction then becomes psi1 times 1s and psi2 times 1s. That is just a product of the eigenfunctions of the component Hamiltonians. And we take its expectation value with the perturbing Hamiltonian, that is the 1 by R12 term. Now, if we are to put in the 1s electrons wave function and compute the expectation value, what we would get is equal to five by 8 times into Z atomic units. And This comes out to be 34 electron volts. So what we know now is that a delta E is equal to 34 electron volts. Now what we can do is to find the eigenvalue of the exactly soluble Hamiltonian. That is the Hamiltonian that is composed of two component Hamiltonians. This is our first component Hamiltonian that takes care of the r small r, that is the component Hamiltonian that takes care of the variable pertaining to the first electron, and this is the Hamiltonian that takes care of the second electron's variable, and we neglect this term. And the eigenvalue for that system can be computed using assuming the fact that when we don't have the R12 term, the system is essentially a hydrogen-like atom system. So it is hydrogen-like, but it is hydrogen-like in the sense that everything is similar except that to a hydrogen system, to a hydrogen atom, except that the nucleus has a greater charge, that is +2. And for a hydrogen-like system, the energy is given by minus 13.6 z square by n square, where z in our case is going to be 2 and n is going to be 1. And since we have 2 electrons in our system, we are going to multiply it by 2. And hence, the eigenvalue of the exactly soluble Hamiltonian comes out to be, if we put in the values of z equal to 2, n equal to 1, as minus 108.88 electron volts. So now we have the actual value as well as the correction. So our actual value is minus 108.8 and our correction is minus 34. And I think there's a correction here in the sense that this correction is positive. And when we take the sum, it comes out to be minus 74.8 electron volts. To put this into perspective, minus 74.8 electron volts is our corrected energy, and the actual energy for the helium atom ground state is minus 79 electron volts. So, using first order perturbation theory, we were able to improve our estimate from minus 108.8 to 74.8, which is about a 5% error between the actual value and the predicted value. Hence, here what we have done is to derive the first order correction to the energy using perturbation theory and improve our estimate for the ground state energy of the helium atom by applying it. Now this estimate can be improved further by taking higher order corrections to this into account, and we can get closer and closer to the actual value starting from the hydrogen like system. Anyway, this is what we covered in this lecture. We looked at perturbation theory and how do we get to the expression for the correction for the first order correction to the energy, and we were able to apply the same to the helium atom system. Thank you.